we always talk about the gradient of a function. So like, I'll name my function f. Well, the notation we use to denote the gradient is this little triangle. If you compare it to like the finite difference triangle, this is like upside down. And so if you wanted to make this symbol in Microsoft Word, what you would type in Microsoft Word is /D delta. If you want to make this symbol using Microsoft Word, use /nabla. So I guess this is called a nabla. But
it's the famous nabla. From Marshall equations.
Oh yeah, sure. And anyways, if I write nabla f anywhere, I'm talking about the gradient of f. And the gradient of a function f, if f is a function of two variables x and y, then this is a vector, and the entries of my vector are the partial derivative of f with respect to x and the partial derivative of f with respect to y. So if you already know how to take partial derivatives, then there's really nothing crazy about a gradient, right? A gradient's just a vector whose entries are the partial derivatives. Okay, so if I have a function g, and g is a function of three variables, x, y, and z, in other words, like g is like a scalar field, then if I write nabla g, or the gradient of g, this is just a vector with three entries, where the entries are partial g with respect to x, partial g with respect to y, and partial g with respect to z. But we've already done partial derivatives. And so if I ask you to take the gradient of a function, that should be super duper easy. That's not anything like difficult. It shouldn't be anything intimidating. So what's important about a gradient is, if I have a surface given by z equals some function of x and y, so this is like a two-dimensional surface living in a three-dimensional xyz space, then the gradient of f is a vector that points in the direction of the steepest ascent. So if you imagine that you're standing on like a grassy hillside, there used to be like a Windows background image that was like a nice rolling hill. But anyways, imagine you're like standing on something nice like this. I blow that up. There we go. So if you're standing right here on the side of the hill, then you can turn around in 360 degrees and face any direction you want. One of those directions is going to make you ascend as quickly as possible, or in as few steps as possible. That's what I mean by the direction of steepest ascent. And so that means if this, surface of this hill is representing my two-dimensional function in 3D space, then the gradient vector of that function is going to point in the direction of steepest ascent. And so for most places, that's going to sort of like point towards the top of the hill. And like over here, maybe it points in this direction. But does everybody do you feel like you get what I mean by the direction of steepest descent? Okay, so what if you have a function of 3 variables? So in other words, like what if we have a scalar field where you provide me the x, y, and z coordinates in space, and I tell you like what the density of the scalar field is at that point in space? Then the gradient is going to be a 3-dimensional vector that points in the direction that the density is increasing the fastest. Okay, so this picture from Wikipedia shows what you call level sets or level curves. And so imagine that this is like a hill, and so this is the top of the hill, and these are all level sets. So these red vectors would then be gradient vectors. And so if you're talking about the point x0 right here, then the gradient vector is pointing in the direction where it's going to ascend the hill the fastest. Of course, the title of this article is gradient descent, so probably what it means is this is more of a valley. This is like a minimum. And so these red vectors would then be the negative gradient vectors. So by subtracting the gradient vector each time you're getting closer to the minimum. Right, so anyways, that is like sort of the meaning of the gradient vector, and they're very, very, very super duper useful. In fact, in our group project that we're going to do after spring break, we're definitely going to be working with gradient vectors a lot. And like I said, if we're talking about a function of 2 variables, then the gradient points in the direction of steepest descent for the output of your function. And if you're talking about a function of 3 variables, then your gradient vector is a 3-dimensional vector that points in the direction that your density of your scalar field is increasing the most rapidly. But this doesn't just, apply to 2 or 3 variable functions. You could have some function of like 5 variables or 6 variables or 7 variables. And if I have a function of 7 variables, maybe I'll name them all x, but use subscripts to tell the difference between my variables. Otherwise, I'll run out of letters to use. Then this gradient is just going to be a vector with 7 entries. Okay? So this would be partial f with respect to x1, partial f with respect to x2, partial f with respect to x3, partial f with respect to x4, and so on. Okay? So you're not limited to the number of input variables you can have in your function. In fact, in our group projects after spring break, I'm going to give you like functions of like 13 variables, I think, as part of the group project, which is, it would be a pain to solve by hand, but the point of the group project is going to be that we use MATLAB to solve these things, and so you're not actually having to do the computations by hand. You just have to understand how it works so that you can tell MATLAB how to do it. Why, do you want to use Python instead? If you use Python instead, that's fine too. Of course, it's a group project, so your group has to decide on what you're going to use. If your whole group wants to use Python, that's fine, but otherwise, you need to use MATLAB.
I know MATLAB is like a prestigious, complicated thing sometimes.
So, okay, so that's what the gradient is. That's what is the gradient. The next question is, what is a directional derivative? And a directional derivative is not a vector. It's a scalar, so it's just a number. It's just a magnitude. And what the directional derivative tells you is this. Basically, you choose a direction, and the direction that you're giving has to be a vector. So we'll say u is a vector with direction 1, 1. So that way you're pointing along the line y equals x in the first quadrant, you're pointing away from the origin. Then we take that direction vector and you have to normalize it. You have to find a unit direction vector, and so I might call this u hat. And if I'm trying to normalize this, it means this is going to be square root 2 over 2, square root 2 over 2 for my entries. That way this vector has a norm of 1. That vector has a magnitude of 1. And then if I want to take the directional derivative of my function f, what I do is I take the gradient of f and I dot product with the unit direction vector. And this is my directional derivative. So you guys know how to do the gradient, because the gradient's just the list of the partial derivatives. You guys know how to, take the normalized something, find a unit vector in the same direction as any vector. And you know how to do the dot product. So that is all a directional derivative is. What the directional derivative is telling you is that if you are standing on the hillside and you are pointing it's not directly in the direction of steepest descent or descent, but if you're just pointing in any direction you want, then the directional derivative is telling you how quickly the values of the function are changing in that direction. So like, how quickly are you moving up or down in altitude if you just start walking in some direction along a hillside? Or, in three-dimensional space, if we've got a function of 3 variables, we've got like a scalar field, then the directional derivative is saying, given a 3-dimensional vector that points in some direction in 3D space, how quickly is the value of the scalar field changing as you move specifically in that direction? Yeah. So, if the direction we happened to choose was 1, 0, then my directional derivative would be the gradient of f dotted with 1, 0, right? And so the gradient of f, of course, would be the partial derivative of f with respect to x and the partial derivative of f with respect to y, dotted with 1, 0. And that would be...
Partial with respect to f.
Yeah.
To x.
It would be the partial of f with respect to x. And that makes sense because the direction 1, 0 tells you that you are facing exactly in the positive x direction. If you did the same thing with the directional vector 0, 1, then you're talking about the direction facing exactly in the positive y direction, and then this dot product would be the partial of f with respect to y. But if you choose any other direction, it's going to be some linear combination of the partial derivatives, and it's going to tell you how quickly the function is changing in that specific direction. For some, let's use polar coordinates for a moment, right? So this is my xy plane, and so I'm going to say theta is this angle. Then my unit direction vector would be cosine theta sine theta. My directional derivative would be cosine theta partial f partial x plus sine theta partial f partial y. There was a dot product formula that we talked about a while ago in like the very first chapter, where if we were taking the dot product of u dot v, this was the same thing as norm u norm v times cosine of the angle between u and v. Okay, so now that we're taking the directional derivative is like a unit direction vector dotted with the gradient vector. And so this should be 1, because that's a unit vector, so the norm should be 1, times the norm of the gradient times the angle between the direction vector and the gradient. So when the directional derivative is maximized, well, the norm of the gradient never changes, but the directional derivative would be at its maximum when the cosine function is 1. The cosine function is 1 when the angle between the gradient vector and the direction vector is 0. And so that means the directional derivative has its maximum when the direction is pointed in the direction of the gradient vector. Does that make sense? Okay, so this phi right here, this is the angle between the direction and the gradient. So this, after we define what the function is, this gradient is relatively constant. So if I want to maximize the directional derivative, the only thing I have to mess with is the angle between the direction u and the gradient. But the maximum value of cosine is 1. Anywhere the maximum value of the cosine function is 1. It achieves that maximum whenever this phi is 0. Right? So cosine of 0 is 1. And so that means I get the maximum value of the directional derivative when the angle between my direction and my gradient vector is 0. So if the angle between the direction vector and the gradient vector is 0, that means the direction vector is in the direction of the gradient vector. So that means that the direction of the gradient vector gives you the maximum directional derivative. And since the directional derivative tells you how quickly your function values are changing in that direction, that means that the gradient is the direction of the steepest descent. Okay, that was a good question. I didn't actually really haven't ever really thought about that before. Okay. The last kind of theoretical thing I'll do. Oh, yeah. Okay. So we're going to save that probably for another time. That's in the next section, anyways. The next kind of theoretical thing I'll tell you about before we start doing some examples of this is that the gradient is normal to level sets. Or a better way to say it would be the gradient is orthogonal. Or you can think about it like perpendicular, if you like the word perpendicular. The gradient is orthogonal to level curves. So if I've got like a little topographical map or a little contour map with a bunch of level curves drawn on here, and I've got this point right here, and I want to say what's the gradient vector? Well, guaranteed the gradient vector has to be perpendicular to these level curves. In other words, the vector has to be orthogonal to the level curves. So this angle will always be 90 degrees. So if you like zoom in really close to where everything looks straight, this point is going to have a gradient vector like this, and that would be the direction of the steepest ascent. And then you have the direction of the steepest descent pointing in the opposite direction of the gradient vector. And then perpendicular to this is the level curve. And again, this really only applies to like differentiable functions or like smooth surfaces. But for like a perfectly smooth surface, if you zoom in, far enough, zoom in really, really close to these level curves, and they're going to sort of look like straight lines, then it should, at least it makes sense to me that the direction of steepest descent would be orthogonal to the line of no ascent, right? The level curve is the line where the value of the functions do not change. And so it sort of lies halfway between the direction of steepest ascent and descent. I can show you the Wikipedia picture again too. So again, these blue lines are level curves. So along each blue line, the function value stays exactly the same. And you can see that these gradient vectors here in red are always orthogonal to the blue curves. They're always orthogonal to the level sets. So, gosh, and this is the really hard thing to imagine or visualize. But what if, instead of having a function of 2 variables, what if we have a function of 3 variables, right? So g is a function of x, y, and z. So that means this is, again, I've already said this a whole bunch, but this is a scalar field. And so all of 3D space is sort of permeated with values of this scalar field. And if I set this function equal to some constant value, like if I set it equal to like 0, then this actually defines a surface, like a 2D surface in space, in 3D space. And this is what we would call a level surface. It's another kind of level set. Like those level curves were good for defining level sets of functions of 2 variables, but if you have a function of 3 variables, then the level sets are actually surfaces that exist in space, because those are the sets of all coordinate triplets, x, y, and z, that give you the same value of your function whenever you plug them into your function. Well, it still works exactly the same way, that the gradient vector is orthogonal to these level surfaces. So as kind of a easy example to help you guys see it, if I have the function g, and it's a function of 3 variables, it's the function x squared plus y squared plus z squared. That means you choose a point in space, x, y, z, and I'll tell you the value of the scalar field at that point in space. That makes sense? But if I set this g function equal to 25, for example, it doesn't have to be 0. This is just any constant. So if I set g equal to 25, what's the shape of this surface given by g equals 25?
A sphere centered 0, 0, 0.
Exactly. It is a sphere with radius 5 centered at the origin. And so, again, this function g is a scalar field, right? I'm saying you can choose any point in 3D space and I'll tell you a value of g. But if I actually set this this multivariable function equal to a constant, like I set g equals 25, then that describes a level surface. In this case, the surface has the shape of a sphere. All the points along the sphere have the same value of the function as the value 25. So if you were to take a gradient vector of this function g, gradient g would be a three-dimensional vector, and it would be the partial of g with respect to x, which would be what? 2x. And then the partial of g with respect to y is 2y, and then the partial with respect to z is 2z. So that means this vector is always going to be orthogonal to the level surfaces. And hopefully that makes sense because, all of the level sets, no matter what constant you choose for the g value, all of the level sets are going to be spheres centered at the origin. This vector is always going to point away from the origin. If you choose that, a point x, y, and z, then this vector just points away from the origin in that direction.
And x equals y equals. Makes sense.
And anyways, if you've got a vector that's pointing away from the origin, then that's going to be orthogonal to the surface of a sphere that's centered at the origin.
Could we graph it?
Yeah, we can try.
Just to visualize it.
Okay, let me see how this works. So, gosh, man, so GeoGebra is convenient, but it's just not, it doesn't do exactly what I think it would do in every situation. So what I can do is I can type in x squared plus y squared plus z squared equals 25, and that gives me that sphere centered at the origin. I don't know how to put in a vector on GeoGebra, but I can put in a line defined parametrically. And so if you've got the vector, well, let me see if I can do a... Can I do a point in space and then drag it? Oh, kind of. Okay. Then let me try to do a line defined parametrically, so like ht, comma jt, comma kt. Okay. Okay, that's about as good as I could expect. So this point in space right here, this little a, is arbitrary. I can just drag it around. Since I define this line by 2 times the x coordinate plus 2 times the y coordinate plus 2 times the z coordinate, you can imagine kind of whatever gradient vector I've got of this scalar field is going to lie in the direction of this line. And then you can also tell that the line should be orthogonal to the surface of the sphere. Right? It's not a perfect visual representation, but let's do an example. Like I told you, your homework was going to be 3 through 27 odds, so let's like start working at number 4 and we'll do the evens in class. So number 4 says we've got f and it's y divided by x plus y. It gives us a point with coordinates 3, 0 and direction of negative pi over 6. And what it's asking is, find the directional derivative in the direction of theta equals negative pi over 6. So since f is a function of x and y, the xy plane is going to be the domain of my function here. And then theta equals negative pi over 6 means it's pointing in this direction. That would be like my direction vector. So if I wanted to write a unit direction vector, I would choose anybody know?
Cosine, sine.
Exactly. So cosine of negative pi over 6 would be root 3 over 2. And then what's sine of negative pi over 6? Negative half, yeah. So that's my direction vector. In that direction, theta equals negative pi over 6 with a norm of 1. And the way you find this is you take cosine theta, and then the second entry in your vector will be sine theta. All right, and then we find the gradient. So the gradient of f is going to be a 2-dimensional vector. And what is the partial derivative of f with respect to x?
Negative y over x plus y squared.
Negative y over x plus y squared? Yep, so you can think of derivative quotient rule. It would be f prime, but we're pretending y is constant, so that's 0, g minus y times the derivative of x plus y, which would just be 1, so that's negative y, and then over the denominator squared. And then what is the partial of f with respect to y?
X plus y minus 1 over x plus y squared.
Over x plus y squared. Okay, so it should just be x, right? Up top. Okay. And now to find the directional derivative, we just have to take the dot product. So the directional derivative, oh, and by the way, my point is x coordinate 3, y coordinate 0. So, like, if I wanted to evaluate the gradient of f at the point 3, 0, this would be the vector negative 0 over, who cares, it's a 0, and then 3 divided by 3 plus 0 squared. So 3 divided by 9, so 1/3. That would be my gradient vector specifically at the point 3, 0. Here's my point 3, 0. So my direction that I'm asking about, remember, is in this direction. The gradient is in the direction 0, 1/3, so the gradient is like this. And I'm saying, let's take the dot product of the gradient and the direction vector. So, this is going to be root 3 over 2, negative half, dotted with 0, 1/3. So, it's going to be negative 1 over 6.